Hello, everyone, and welcome to today's webinar, Preparing for the Worst, the Resurgence of Respiratory Infections. I'm Cassie Soltman of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Diasorin Molecular, LLC. To learn more, visit molecular.diasorin.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. I'd like to now welcome our speaker, Dr. Michelle Tabb, Chief Scientific Officer at Diasorin Molecular. Dr. Tabb, you may now begin your presentation.
Okay, thank you very much for that great introduction. And I'm so happy to be here presenting with you all today. Let's talk about what's happening right now with the respiratory season, especially as we enter into this third year of the pandemic. And so with that, let's go over today's objectives. So hopefully by the end of my talk, you will understand the current trends in the respiratory illness in this third year of the COVID pandemic. We'll also take time to review the theory of viral interference and some other factors that can actually be shaping the resurgence of certain respiratory viruses. And then lastly, we will discuss why detecting and differentiating respiratory pathogens is really important for treatment and isolation strategies. So in terms of the talk's agenda today, we'll start by talking about respiratory virus seasonality, sort of how it was before the pandemic, and then the impact the pandemic has had on virus seasonality. And next, we'll talk about a theory called viral interference. We'll follow that with some trends in this current respiratory season, especially in the Northern Hemisphere in the 2022-2023 respiratory season. And then we'll talk specifically about one of the big viruses of concern that has surged, and that is RSV, or respiratory syncytial virus. I'll also talk about some re-emerging respiratory pathogens, and then we'll end by talking about multiplex detection and differentiation of respiratory pathogens. So let's dive right into respiratory virus seasonality and then talk about the pandemic impact. What impact has COVID-19 had on what we would have seen typically before the pandemic? And so this slide contains a figure here that demonstrates that. And so this figure shows the typical seasonality that we would see. We have winter viruses, summer viruses, and some that are present all year long. And so the winter viruses that we know quite well in the Northern Hemisphere, at least, we think of RSV, flu A, and flu B, and those are shown at the top. We have some viruses that we see usually only during the summertime, and those include viruses like non-rhinovirus enteroviruses. We also tend to see some viruses all year long, like human metapneumovirus or rhinovirus, and then some type-specific viruses like influenza virus sort of come and go depending upon the time of year. And then we have all-year viruses like adenovirus and human bocavirus. And so that's the typical seasonality, at least up through the pandemic. But then the pandemic hit. And so now one of the big questions is what will happen to the seasonality of these viruses? But then also, what about SARS-CoV-2? So now that things are starting to calm down, so to speak, will this end up also being a seasonal virus? And so I think we wish we all had a crystal ball. I think we don't know that yet. But let's talk about some of the other things that we observed during the pandemic when there was such high case counts of SARS-CoV-2. So we'll start by talking about what we saw in children less than 2 years old. And so this publication really highlights that. We saw the complete disappearance, really, of certain respiratory viruses like RSV, influenza, metapneumovirus, and paraflus. In 2020, that's what happened, disappearance. In 2020-21 season, we also saw a reduction of other respiratory viruses like adeno, boca, and enterovirus. But there were a couple where we saw absolutely no significant difference in the prevalence, and that includes rhinoviruses, some of the non-SARS-CoV-2 coronaviruses, as well as other viruses like CMV. And so the chart on the left shows that big drop. So the bar goes up and up. until 2020, and then significantly drops. Those are just the case counts in children less than 2 years old there in 2021 season. So one of the conclusions of this study, obviously, is that we had a striking reduction in hospitalizations, in viral cases, and then in hospitalizations and lower respiratory tract infections, and a modification of when these viruses were showing up, what time of year. And very interestingly, it seemed that the enveloped viruses were mainly affected. So that could have been one of the clues there into why some viruses continued to appear while others disappeared. So what happened with flu? And so on this particular slide is data from the CDC. And what I've done is broken it into pre-pandemic influenza in the US. And then that's on the left in the 2019 to 2020 season. And then on the right, we have the 2022-2023 estimates based on the data that's already come in through the end of December of 2022 at the CDC. And you can see there that the case counts for the 2019 to 2020 season were between 39 to 56 million total flu illnesses in that particular season. Flip over to the right-hand side, and we are on par to have a season just like we did pre-pandemic. So flu levels have not only come back, but they've come back to be just about basically where they were before the pandemic, showing up there at about the 22 to 43 million case count estimates, at least from the CDC. But what about other viruses? And so this is flu, once again on the left-hand side, and it shows quite nicely this data from the CDC that there was a lot of testing in the 2021 season, shown there by the red arrow, which is that shaded blue part of this chart going up. But the black bar shows the total number of positives for flu was basically non-existent. Another virus here, which is on the right-hand side of this chart, para-influenza viruses, they remained at a very low rate, less than 1% positivity, but by May 2021, their prevalence also started to increase up to about 10%. You can see that bar starting to go up, that dark blue bar shown there right above the red arrow. We saw RSV also drop to record lows, almost undetectable. And that's shown on the left-hand side chart. Of course, a lot of testing for it. But then you can start to see the blue line actually come up with RSV cases. And we certainly have had an RSV surge occur. So RSV spiked nationwide, especially in the south of the US, and it happened sort of in an unlikely season in the spring to summer of 2021. And that's this first peak that's seen on the left-hand side of the slide of the chart that's on the right. And then we had a lull once again during the summertime, and then we have really been walloped by a big RSV surge now, starting kind of early into the summer fall season here in 2022. And we'll talk a little bit more about RSV later in the talk. But what happened with the common cold virus activity? Well, it continued. And what I mean by common cold virus activity is rhinovirus, enterovirus, and adenovirus, which continued to circulate among children during the pandemic. Non-SARS-CoV-2 coronaviruses also were circulating, although there was a little bit of a delay there. And so if you look at these charts, we have the rhino-entero on the left. We have the adenovirus there present, but at low levels in the middle. And then we have this delay in the other non-SARS-CoV-2 coronaviruses, but you can see the blue lines start to peak up at the end of 2021. And so if we just look at all the data all together, the chart on the left kind of tracks this. So if we start from 2017 and we look at the comparison of percent children positive for viruses over all of these seasons, up at the top is RV, EV, that's rhino and entero. You can see there about 30% positivity in kids over all of these seasons up through 2021. But compare that to what you see for RSV. So before the pandemic, rates at 16.7% or higher, and then, wow, it goes all the way down. It drops to the low of 1.2%. The similar picture is there for flu, which dropped to 2.6%, and just other respiratory viruses in general dropping down from like that 15% down to 6.1%. So why was there this drift? And what I mean by drift is a shift in where we started to see viruses come up again, different from their typical seasons. Well, Of course, the transmission mechanisms were reduced. We saw temporary lockdowns and virtual classes, social distancing, PPE, and of course, reduced travel. Those could have all been factors causing this drift. But what about the persistence? And here is where I want to bring up the non-enveloped viruses like the rhinos and the enteros, which persisted despite all of these transmission mechanism control mitigations that were in place. Well, non-enveloped viruses actually stay for prolonged periods of time on surfaces. They survive a lot longer than their enveloped cousins. And they're basically less susceptible to prevention and transmission from mask wearing or from soaps or sanitizers. And there's a lot greater asymptomatic transmission. In fact, what's underappreciated sometimes is the amount of rhinovirus asymptomatic transmission that there is globally. And so these are just some theories about why these trends happened during the pandemic. But when we think about when one virus is dominant or present versus another, there are other mechanisms at play here. And so this slide lists some of those mechanisms of respiratory viral dominance. So of course, because of social distancing, travel, et cetera, movement restrictions, we saw a lot of typical respiratory viral activity and transmission decrease. And so it was a hit across the board, so to speak. But then they've come back. So of course, one of the questions is why? But also for respiratory dominance here, let's talk about flu. So interestingly, historically, when a novel flu has emerged and has become pandemic and sort of taken over the planet, whatever was circulating there in the flu family beforehand basically disappears. And that pandemic strain replaces that flu strain or those flu strains that were circulating at the lower levels and becomes the dominant strain. And this happened actually starting from H1N1, which was circulating, Spanish flu, early 1900s. And then in 1957, it was replaced by H2N2. And then in 1968, H3N2 replaced H2N2. And then in 2009, we saw once again H1N1 replacing the H3N2. And when we see this for flu, for example, that dominance of a respiratory virus, it might occur when the global population has never seen that virus before in terms of their immune system seeing it, what we call being immunologically naive. And here is where a viral interference or a temporary immunity could be induced by that prevalent, predominant viral infection. Okay, so whereby one infection with a respiratory virus sort of limits the infection and contribution from any other viruses that might want to circulate and infect. Of course, there are also seasonal impacts on respiratory infections. And so we have, the impact of, what is the temperature outside? What is the sunlight? What is the relative humidity? And that goes for inside and of course outside. So absolute humidity and relative humidity are both kind of important factors. And then as we move indoors when there's colder weather, then of course, relative humidity also comes into play. And if you've heard of droplet theory, that's something else we need to think about in terms of viruses and their ability to transmit, because the amount of virus that's present in a droplet, how far those droplets can be distributed, how dry or wet the air is that we're breathing, of course, all come into play with how transmissible that virus might be in those droplets. Add to that, if the weather's cold outside and we have people coming together to celebrate indoors together. And so certainly there's that social aspect, the contacts that people have in terms of transmitting viruses to one another. There's also, of course, the factor of the human hosts themselves and their immune state, which come into play here, that can also have an impact on respiratory infections. But the two major contributing factors are the changing environments and seasons, and of course, those human behaviors in terms of transmission and seasonality of some of these viruses. So that leads me to talk about something that I already mentioned in more detail, and that is viral interference. And this is the theory that one virus can basically cause an impact downstream that prevents infection from other viruses. And so when we typically think about viral infections, a lot of times we're thinking, 1 + 1 = 2, or maybe even 1 + 1 = 10, depending upon if we're talking about severity. So for example, when someone's infected right now with SARS-CoV-2, and then they do have a flu infection on top of that, obviously that infection can be extremely severe. So that is a positive type of interaction. Even though it's not positive for the patient, it's positive in terms of its severity. But viruses actually frequently negatively interact, and that is a phenomenon known as viral interference. And this is when a primary virus infecting a cell prohibits the infection of that same cell by another secondary virus, or even by more viral particles of that same viral type. And so there's a pictorial representation of that here in the figure, where we have a virus coming in, infecting a cell, moving over to the right-hand side. Now that infected cell basically gets some body armor and deflects additional infections by other viruses. And so that's sort of a basic and simple principle here of what viral interference is. If we could understand the mechanisms of how this happens, this might be a basis for developing some new antiviral treatments. And with that, let's talk about the historical evidence for this actually occurring. So in the 1960s, there were live enterovirus vaccines that were used in some clinical studies in children. And when those live entero vaccines were used in those kids, it was noticed that there was decreased detection of unrelated respiratory infections in those kids after they had received those injections. And the reduction came in terms of reduction in flu cases in those kids, as well as paraflu, RSV, rhinovirus, and adenovirus infections in that study. In the 1970s, there was a study in India and Nepal that found that adenovirus types tend to be prevalent in a particular village, and there are no other adenotypes circulating but that one. And even that one might differ from village to village. So there seemed to be some kind of an exclusion happening even amongst adenovirus types. There was a study performed in Norway between 1974 and 1981 that analyzed the respiratory infections in that country. And they showed that RSV and influenza infections did not reach their epidemic peaks at the same time. Now, of course, this seems a little obvious to us now because we're always used to now seeing, at least pre-pandemic, a peak of RSV followed by flu A and flu B. But at least that analysis in Norway showed that that kind of a pattern of different viruses peaking at different times has been present for a long time. And then in 2009, 2010, we had pandemic H1N1 circulating the globe. And there was RSV present at that time, which basically dropped down extremely low, almost to zero, when pandemic H1N1 took over. And then there's a theory and some evidence that rhinoviruses might have interrupted the spread of that H1N1 flu virus during that pandemic. So rhino, especially here, I want you to remember, because there is a disruption there that could have happened of flu. So if we look at other evidence, there is a lot of it. This chart is basically meant to summarize all of that. And this paper from Perret and Boivin actually looks at what was the interfering virus that impacted that second virus. And you can see the arrows there. We have the rhinovirus impacting the influenza A virus. And then there is also evidence of rhinovirus that is disrupting SARS-CoV-2 infection. And these evidences are coming from different types of studies, both from epidemiological, historical, active studies, as well as cell culture and animal models. So my question here, and one of the questions that some authors on some studies have asked is, if rhinovirus was seen to interfere with the replication and spread of pandemic influenza virus, as we saw in that evidence back in the swine flu pandemic 2009-2010, could it do the same thing for the current pandemic strain, SARS-CoV-2? And there's one key word there that's in that question, and that has to do with interferon sensitivity. So interferon is a signaling mechanism that we'll talk about in the next couple of slides. And there is evidence that this is actually what's happening. And so there was a study of 800,000 adult patients with cold symptoms in the previous year before the pandemic. And it found that those patients who had experienced cold symptoms, and let's assume that those cold symptoms were from common cold viruses like rhinovirus. Those patients that had had a rhino infection in the previous year leading up to the pandemic were less likely to test positive for SARS-CoV-2. Additional evidence has come from some studies that have, that by Chamirla et al., that has shown that patients that had had a rhinovirus infection before or early in the pandemic had a jump starting of their interferon stimulated gene response, their innate immune response, and that response, that interferon response, actually negatively impacted SARS-CoV-2 viral load. In other words, if you had rhinovirus infection, it really limited the impact and actually even replication of SARS-CoV-2 infection-causing particles in patients. And so that's what we mean by viral interference. So what causes viral interference? Well, I've already alluded to the interferon response, but there's also just some basic direct competition between viruses that can go on. But let's talk a little bit more detail about the interferon response. And there's a graphic here on the right-hand side of the slide that shows exactly what is meant here. So there's a viral infection. That virus goes into the cell, and it confers sort of an antiviral state in that cell that's part of our innate immune response. The detection of the viral RNA, once the virus is taken into the cell, it causes infected cells to secrete interferons, and that's sort of like a neighborhood watch system. And so that signaling system alerts other surrounding cells that there's a viral infection going on in this cell. That release also upregulates interferon stimulating genes, ISGs, and they encode antiviral proteins that block virus from entering cells, block viruses from leaving cells, and shut off cellular machinery required for replication. So a virus gets in there, starts hijacking the cellular machinery, starts replicating like crazy, and then also the cell enters this antiviral state at the same time, sort of deflecting other viruses and maybe even preventing them from getting in and conferring an advantage to that first viral infection. So there's a whole cascade of events that happen, and it's shown in the graphic on the right-hand slide, but I'm not going to go into detail on that today. So interferon response could cause viral interference. There's also, though, this just general direct competition between viruses. And the competition is, of course, between cells to infect, cell surface receptors, if they use common receptors, cellular resources, and back to replication. Well, faster replication, the faster hijacking of the cell wins the battle. So the first virus to win that battle causes the cell to enter an antiviral state, and it really limits that second viral infection. So the authors of this paper, Chamirla et al., have looked into this, especially between rhinovirus and SARS-CoV-2, and they have put out a model for this viral interference. And a quote from the paper is, heterologous innate immunity, that is the interferon response, causes a subset of individuals who are refractory to infection during periods of high respiratory virus circulation. So in other words, if people had a rhinovirus infection, it conferred this protection to them. So even though COVID was circulating rampantly during the pandemic, there were certain individuals who were protected from getting that infection. So with that, what are some future areas of study? And so certainly looking at deficiencies in interferon production in a patient or in individuals, we want to look into that to see if those individuals are more, if those with low interferon responses are more prone to getting co-infections or more severe disease, or more severe clinical outcomes and things like that due to co-infections. This will be the first winter in the Northern Hemisphere where we're going to actually start to see some co-infections based on that data that I showed in the first part of my talk, since a lot of viruses are coming back. But it might take several seasons for us to finally see and observe the clear patterns that are going to be taking place. Viruses causing asymptomatic infections could be key players in this viral interference. And as I mentioned, rhinovirus causes a lot of these asymptomatic infections. And two quotations I wanted to read that come right out of the paper here. So we have Pablo Murcia from the Glasgow Center for Virus Research, and he said, most of what we know about virus infection, virus pathogenesis, virus epidemiology, it's based on the one virus, one disease approach, and that's not real. And you know, it is not real because viruses are circulating in our environments all the time. And even during COVID, although COVID was the most prevalent virus, there was still other viruses circulating. And certainly these have impacts on one another. The situation's much more complex than maybe we would have originally thought. And then a quote here from Ellen Foxman from Yale: anytime you have an expansion of the paradigm of how you understand disease pathogenesis, this opens up the door to interventions that you'd never even thought of. And so this leads me to the next slide, which is, what about virus interference used for infection prevention? And so many people are starting to think about this general interferon response and how we could maybe use it in the future so that we can study it and also develop antivirals. And so there was a paper that came out early in the pandemic actually asking a question: can existing live vaccines prevent COVID? This was based on the theory that if you gave, say, oral polio vaccine or any of the other live vaccines, because it's a live viral infection, an interferon response is induced. And so that general interferon response, but does it make somebody less susceptible to subsequent viral infections like by SARS-CoV-2? And so there are some trials looking into this exact thing right now. We have live vaccine trials against COVID. There's 5 trials testing actually the tuberculosis BCG vaccine in this way. There's 2 trials testing oral polio vaccine and 2 trials testing the MMR, the measles, mumps, and rubella vaccine, looking to see, once these live attenuated vaccines are given, challenge those patients or track them to see if they get subsequent infections at a higher or lower rate than without these kind of interventions. And so we'll have to wait and see what happens with these kinds of interesting studies. So now let's switch to talk about the trends in the current 2022-2023 respiratory season. And so let's begin with the influenza update. So what's happening right now with flu? So this is a snapshot as of the end of December, and this is based on the CDC data. And so what we have seen is that we have had a large flu season, right? We're back on par, as we saw in the beginning of my talk, with what we saw pre-pandemic. The hospitalization rate, however, is about 4 times higher than the highest rate observed during this same week, and actually since like more than 20 years ago. We've seen a lot of pediatric deaths, and this seems to be an age group where there's more severe impact. We also see that we have more H3N2 than H1N1, and we'll talk about that more in a moment. But you can see there that the graph on the left, at least the CDC tracking, is showing that we might have hit our peak an earlier season than we've seen in the past, but we might have already hit our peak and it's coming down. But there's still a lot of hotspots across the US. And all of this data does not include the post-holiday period reporting. And so stay tuned and we can keep checking in with the CDC data to see what happens post-holiday period. Switching over to a similar update that's provided on the European Union from the ECDC and WHO Joint Influenza Update website, and they saw something extremely similar. They continue to see about 34% of specimens testing positive for flu for the week ending January 1st. And just as we did in the US, we saw an earlier influenza epidemic start than the previous 4 seasons. This was actually predicted by what we saw in the Southern Hemisphere. As we know, when we look at things like flu, we're always looking to countries like Australia and their great tracking to help us predict what's going to happen in the Northern Hemisphere. They saw an early flu season. They also saw a big pediatric impact with more severe illness in that patient population. And we're seeing the similar things here in the Northern Hemisphere. Now let's hone in on what's happening specifically with influenza this season. And so of the influenza A type circulating so far, looking at October to December, we see about 30% are H1N1 type, and they're a specific type of pandemic derivative strain called 6B1A5A2, and about 70% are H3N2. The good news is that the vaccine strains are a very good antigenic match to these particular viruses, these flu A viruses. And also the good news is that all viruses that have been collected and tested thus far are susceptible to influenza antivirals like oseltamivir, for example. And you can see there in the right-hand side box that I've highlighted in red there, you can see that sort of 70-30 split in terms of the flu A strains that are circulating so far this season in terms of surveillance. So one note I wanted to make, though, is that diagnostic test manufacturers need to be diligent and alert for viral mutations that may affect detection. So we have heard about some impacts on certain tests that are available today, molecular tests for flu, specifically with the H1N1 strain, that 6B1A5A2 strain. And so, one thing is for certain, flu will change. It's an RNA virus. We have antigenic shift and drift happening. We constantly have mutations that appear in that virus. And so, at least for our company, where I'm at, so for DiaSorin Molecular and Luminex, we constantly are surveilling the databases with the available sequences that are out there for influenza strains and other respiratory viral strains, and making sure that our products continue to be able to detect those strains despite sequence changes. And so, at least on the DiaSorin and Luminex side of things, we've already checked all of our targeted testing products as well as our multiplex syndromic panel target products for to make sure that they can detect this H1N1 strain that's circulating now. And I'm happy to report that they all do. But we as an industry also need to keep up that kind of vigilance to make sure that we're continuing to detect and have that good performance to catch these infections. So now, carrying down a little bit further on the slide, let's switch over to talk about what's happening with influenza B. So we do have influenza B circulating again, but what we have seen are cases of the Victoria lineage. There are two different lineages, Victoria and Yamagata, but why I have that red arrow there is pointing to the fact that there has been no incidence of Yamagata lineage flu Bs detected so far this season. And in fact, flu B Yamagata has not been seen since March of 2020. As I mentioned, these two types of strains or genotypes of flu B typically alternate predominance. When one circulates, we might see some worse or more severe illness in certain age groups versus others. But in general, we have seen these two. And for the last couple of years, though, we've seen a dropout of flu B. So what has happened to this strain, and could it be extinct? The answer is yes, maybe. And why could it be extinct? Well, it turns out that there's some basic differences between these two genotypes or strains of flu B. We have a lower effective reproductive number in the Yamagata lineage than we do Victoria, meaning it has a growth advantage. We have no animal reservoir for flu B. So flu A, certainly we see that in swine and also in birds, as well as humans. And so there's always a reservoir circulating, keeping that virus, active on our planet. But flu B, that's not the case. There's no animal reservoir. So we also at the same time have a great quadrivalent flu vaccine that covers, the H3 and the H1 types of flu A, but also has had Yamagata and Victoria vaccine coverage within it. And so we've also had very nice uptake of flu vaccination. And so high vaccination coverage has induced that broad immune protection. And that kind of coverage can lead to eradication of flu B. And the other thing that happened here is that with the pandemic, it coincided with the time of Yamagata very low prevalence. And so all of these pressures kind of evolutionarily at the same time could have actually wiped out flu B Yamagata. So don't have a crystal ball, but so far, and you can see there the annotations on the papers that have talked about this, it could be extinct. And so let's cross our fingers that we're able at least to wipe out this particular strain of flu B. Let's take a look really quickly at avian influenza. So while the pandemic was happening all around the globe and we started to see flu A cases come up again, and certainly RSV surging, influenza was still circulating in birds, and avian influenza has always been there. There's been some really great surveillance programs going on from the CDC and the ECDC, but they've continued to detect H5N1 in wild birds and poultry. And that has been in late 2021 through 2022. Luckily, there's only been 2 human cases, one in the US and one in the UK. And looking at this strain, the risk of transmission to the general public is extremely low. And I want to remind everybody the reason for that is H5N1, it needs a certain type of cell surface receptor in order to gain access to cells. And so H5N1 is specialized in terms of the sialic acid receptors that it can bind to on bird cells, okay? It would need to change to become adapted, a better fit to human cells to gain entry and cause a pandemic. And so it hasn't done that yet. And so that's why the risk of human transmission is especially low. But people still work with birds and have high exposure to it. And so it's good to know about it. And because of that, there's monitoring programs. You can go on the CDC website. You can see in their surveillance how many wild birds, how much poultry, and in humans where this virus has been detected. But there was a story coming out and a warning just from CDC in November. We have a record number of avian influenza outbreaks right now in both wild birds and poultry. So certainly this is one to just keep looking after. What else is happening? Well, of course, we still have SARS-CoV-2 and COVID circulating. The latest variant of concern is XBB.1.5, and it is rapidly transmitted, and it's starting to account for a higher and higher number of new confirmed cases in the US. There are not as many cases in Europe, at least not yet, but of course, these things can constantly change, especially after the post-holiday period. This is a relative of XBB. It's a recombinant of Omicron and the BA.2.75 subvariant. And as I mentioned, it's very transmissible. It seems to have a growth advantage. It is not causing a major surge in hospitalizations, though, and that's the good news. However, the other good news, I'd say, is that the bivalent booster, that's the Omicron booster, so to speak, it affords really nice coverage of this particular variant that's circulating, okay? So that's the good news, is the bivalent booster. The bad news, and maybe why we can expect a lot of cases from this variant, there has been very poor uptake of the bivalent booster, probably due to a lot of different factors. But here are the statistics right from the CDC website, at least as of this first week of January. So we have only about 38.1% of people over age 65 who've had this booster, and only 15% of ages 5 and up. And so there's a lot of people who could be sort of under-vaccinated, so to speak, and not protected from catching this variant. And of course, we have what's going on in China. We have the Chinese government lifting the COVID restrictions in December. Early December, they had a very effective zero COVID policy. They actually only had reported about just over 5,000 deaths, but then they opened up and they stopped these restrictions. And so with that, there's been some modeling that predicts that there could be a huge amount of cases, a huge surge in China, and a huge amount of deaths, maybe even over 1 million deaths. We're also not sure about the true reporting and the numbers. And of course, we've had countries that are extremely sensitive to cases coming into them from China. An example is Northern Italy, where that was the second global hotspot in the world in the SARS-CoV-2 pandemic, right? So there was a story that came out in December that passengers were tested on 2 different flights that arrived from China coming into Milan, and over 50% of passengers on 2 of those flights were SARS-CoV-2 positive. And so now we've had mandatory testing reimposed for people coming from China into certain countries right now. And so we'll have to wait and see what happens here. China has a very vulnerable population. Their boosters are not necessarily up to date, even though there was large vaccination campaigns initially for the original versions of SARS-CoV-2, and they have a large elderly population as well. And so this is of concern for sure. Okay, we will switch now to talk about another respiratory virus that has been circulating that I've already mentioned, and that is respiratory syncytial virus. And so this virus is an enveloped single-stranded RNA virus, and it is a major cause of global respiratory illness. And I think to some degree, maybe an underappreciated cause globally of respiratory illness in a lot of populations. It's a mainly upper respiratory pathogen, and but it circulates in humans only. This is another case where there's not an animal reservoir. There's 2 different types, flu A and flu B, not flu A and flu B, RSV A and RSV B. But there are some high-risk populations that I wanted to highlight right now. We see a lot of RSV in infants and young children, and that's usually how people know about RSV. But we also see the elderly population, the over 65s, that are especially vulnerable to RSV as well. The most common cause of bronchiolitis globally is the RSV virus, and it circulates with ease, especially in places like daycare centers. And one important thing to note also, previous infection with RSV does not convey persistent immunity, meaning you can get this virus again and again and again throughout your life. So as I already talked about, what happened during the pandemic? Well, we saw initially during the pandemic that there was really no RSV, but as soon as we had pandemic restrictions opened up, we saw RSV come back. And so over on the left-hand side, as pointed out by the red arrow, we saw RSV returning in June of 2021, and then it went down again. But now, starting from the summer of 2022, we have this second where the second arrow is increasing here with this red line here. We had this big surge in RSV cases starting from the summer of 2022. And it has now come down, which is the graphic representation here on the very right-hand side. We finally have started to see it come down. And so that is good news for sure. But it certainly was a big burst of RSV. So even when we think about treatments and strategies right now, I mean, there are some things available. Most are for infants who are at high risk, like this FDA-approved monoclonal. There's also a long-acting antibody shot for newborns, which should cover babies for the first 6 months of their lives. That's gotten FDA breakthrough designation, and also is already approved in the EU, in the European Union by the European Medicines Authority. And there's some really interesting things that are under review now at FDA. And this is because, infants, especially babies, they have really naive immune systems. And so just vaccinating them with RSV is not a very good protection strategy. And so that really opens the door here for what is an effective strategy for vaccination. And that is vaccination of pregnant women. And this is because they will elicit an immune response, and they will be able to transfer those antibodies to their developing baby. This strategy has actually been used for other infections such as tetanus and whooping cough. And so it's something that we can really look forward to, hopefully making an impact on the amount of RSV that's circulating, at least in that infant population. But vaccination approaches for pregnant women and then actually for older adults are also taking place. And so there's been a lot of recent progress. This is a little bit of history about RSV vaccines. In the 1960s, there was a first go at it, but it failed, actually. There was an enhancement of disease. In the 2010 timeframe, though, there was a big development at NIH when researchers determined the structure of the RSV virus's two key surface proteins, the F and the G proteins, and that then allowed a lot of focus to happen on those surface proteins for effective strategies for vaccinations. And in the 2020s, there's several RSV vaccines in clinical trials, not just for pregnant women, as I mentioned, but also for seniors. So we have Pfizer and GSK testing in both those populations. We have the Janssen, J&J, and Bavarian Nordic developing for adults over 60. Moderna is in clinical trials and late-stage trials for adults over 60. Vaccines for children are much earlier in the pipeline, but at least we're seeing some positive things and positive developments and progress happening for RSV vaccine these days. So let's switch to talk about some re-emerging respiratory pathogens. So this goes beyond just talking about what we hear about in the news all the time, which is the flu and the RSV, for example, on top of SARS-CoV-2. Other non-influenza and non-RSV respiratory viruses are also back. We have seen the non-SARS-CoV-2 coronavirus has come back. We've also seen human metapneumovirus come back, and adeno, as well as parainfluenza 1, has started circulating again. And so I want to hit on a couple of viruses that are maybe linked to some reappearance and reemergence during the pandemic and that could be of concern. And so one of them is adenovirus. And so adenovirus is a big family of viruses. There are some that have cause respiratory infections, and there are others that cause GI illness. But I wanted to talk about one, adeno41 here, that's associated with GI illness, but I wanted to do so in context of the pandemic. And this is because during 2021 timeframe, we saw worldwide about 1,000 cases of unexplained hepatitis in children and 22 deaths. And this was reported by the WHO in 2022. And they were trying to find what was the linkage here. Was this virus actually causing the impacts in this hepatitis in these children that they saw? And how could that be related to SARS-CoV-2? Well, there was this publication that is pretty recent in September 2022 in the Journal of Pediatric Gastroenterology and Nutrition, and it showed a link between SARS-CoV-2 and adeno. And the authors hypothesized that liver manifestations they saw, the hepatitis, were because of a post-infectious immune reaction in patients who'd had SARS-CoV-2, but now that subsequently got an adeno-41 infection. And so I'm highlighting this just to bring up the fact that we still haven't seen the damage or whatever SARS-CoV-2 has caused in patients who've been infected by it that will be longer lasting, and that still might show itself once we get subsequent respiratory or other types of infections. And one case here is adeno-41. Switching over to a de facto respiratory virus, let's talk about enterovirus D68 or EVD68. And so there certainly was an increase in respiratory illness among children and adolescents in the last summer's timeframe, July to September of 2022. And the chart from the CDC at the bottom there shows the arrow there in red showing that peak of EVD68 that was seen. And really there was very low incidence of EVD68 due to the pandemic. But in 2022, there were more acute illnesses. There were hospitalized pediatric patients with severe respiratory illness, and those patients were positive for rhino-entero. Sometimes the tests can't differentiate, but certainly there was a lot of evidence here that it was enterovirus D68. Okay, so let's switch to talking about a different respiratory virus here, enterovirus D68 or EVD68, because it's also of concern here because starting in the summertime of 2022, we saw it come back as well. And so there's a chart there on the left-hand side from the CDC, and you can see the red arrow showing the big peak in enterovirus cases that have been seen. And the big concern here was that clinicians started noticing more acute illness, especially in pediatric populations associated with infection. And those were detections of rhinovirus, enterovirus, because sometimes some of the tests don't differentiate within this viral family. But these clinicians alerted the CDC because there was this increase in severe illness. And why this happened was likely due to this extended period of low EVD68 circulation that could have been because of the pandemic. But because of these concerns by clinicians, there was a CDC health advisory notice sent out, a HAN, about acute flaccid myelitis or AFM, because there has been an association seen between EVD68 and AFM. So what is AFM? It's a nervous system disease. It's characterized by rapid onset of weakness in one or more limbs, a la poliovirus. And as of January 4th of 2023, there's been 37 confirmed cases in 22 states, just in this recent sort of outbreak that has happened. Overall, since the CDC began their tracking many years ago, there's been about 716 confirmed cases. And you can see on the chart on the right-hand side, these cases of AFM coincide with the typical every 2-year or so peak of enterovirus that is typically seen in the late summer or fall months, especially in the pediatric population. And that's what's shown here by these red arrows that I've added to the chart. And the far right-hand side, you can see that these cases have started to come up again. Of course, maybe shifted a bit because of the pandemic, but still it's coming back. And so this is another virus that's transmitted by the respiratory pathway that we're going to want to keep our eyes on. So another concern is group A strep, which we do think about as a respiratory illness, but there's also been a CDC recent health advisory notice that's gone out about an increase in pediatric invasive group A strep infections. And this has not just been in the US. Actually, since September of 2022, European countries like Ireland, France, and the Netherlands and Sweden, as well as the UK, have reported an increased number of cases of invasive group A strep disease among children less than 10 years, and actually even a couple of deaths. And we've seen several cases that are several-fold higher than in those pre-pandemic levels. So there is some concern about this for sure. And as I mentioned, we've also seen an increase in the US. The likelihood here is that it's associated with this increased circulation of respiratory viruses in general. And so, of course, when that damage is done by respiratory viral infection, then we see group A strep coming in, and it may increase the severity of infection and be leading to this risk of invasive disease. One particular note here, we continue to have some supply chain impacts from the pandemic, and also because there's been so much respiratory viral illness of late, especially in pediatric populations. There's been an American Academy of Pediatrics notification that recently went out in November. There's been an amoxicillin shortage. And so this is really a terrible time for that kind of a shortage, but, is because there's so much infection happening now, respiratory infection in pediatric populations. Another respiratory virus that I wanted to mention and we should watch is measles. And this is because there have been two recent outbreaks, one in Ohio, one in Minnesota, where we've seen a great deal of cases. And measles is really a severe respiratory infection. Yes, it's vaccine preventable, but you can see the complications there at the bottom of the chart. But first of all, how it spreads, of course, person to person in aerosols, but it's one of the most contagious respiratory virus diseases. It seems that the virus lingers for hours or days following the time that somebody could be around in a room. And so it's really easily spread to different people who are in proximity with somebody, or even come into proximity of areas somebody was in who's had the virus. 1 in 5 people can be hospitalized with pneumonia, and it can be really severe and cause severe disease, not only in children, but in adults as well, especially unvaccinated. There's complications in pregnancy. You can have encephalitis and also death. And, the concern here is not just that there's been some recent cases, but there has also been a trickle of cases on and off from unvaccinated populations, right? We've seen or heard reports about some cases in Disneyland, and that's usually from travelers coming in from outside the US who are unvaccinated. But certainly these cases are of concern. And one of the big reasons they're of concern is because there's been a pandemic impact just on vaccination schedules. And it's estimated that like 25 million children worldwide missed their first measles vaccine dose through routine vaccination in 2021. And even about 15 million more missed their second dose. And that's according to the MMWR in November. And one thing with measles, just like other types of viruses, we need herd immunity in order to achieve this, protection of people, especially those that are immunocompromised, and also to keep the virus at bay. And we need 89 to 94% vaccine coverage to have that for measles. Before the pandemic, we were already on the downslide. We were already at 86%. 2021, it was estimated we're at 81%. And so the WHO and CDC are deeply concerned about this declining coverage rates of the measles vaccine. And there's a paradox written there by the WHO Director General. The paradox of the pandemic is we put all this force behind developing vaccines so quickly for COVID-19, but yet other vaccine preventable illness that actually sometimes still needs some, energy behind global vaccination campaigns, such as measles, have really been forgotten, and vaccinations have been missed. And so we really need to keep our eye on this one and expect to see more measles outbreaks in the US and globally until we can improve this vaccine coverage everywhere. And so with that look at kind of some of the re-emerging and emerging respiratory viral infections that are happening as we come into this third year of the pandemic, I now want to switch to talk about multiplex detection and differentiation of respiratory pathogens, because I know that it's generally accepted now that molecular methods are actually a gold standard to detect respiratory viral infections, whether or not there's just one virus causing the infection, or if there are several that are prevalent at the same time. Some might have similar symptoms that need to be sorted out because there are different treatments based upon which virus is detected. And so here, let's go through the CDC guidance for clinicians when SARS-CoV-2 and influenza viruses are co-circulating, because there's some decision points that should be made in different patient populations for the approach to testing using molecular multiplexing. And when I mean molecular multiplexing, I mean standalone molecular tests. I also mean mini panels that maybe have 2 or 3 viruses that cause similar symptoms, but I also mean molecular panels that could be much bigger, on the order of 16, 20, 25 viral and bacterial pathogens testing at the same time, those molecular syndromic panels. And so in the case of this situation here with the CDC's recommendation, a patient presents to the outpatient or emergency room. These symptoms for flu A, flu B, RSV, and COVID, they're extremely similar and hard to differentiate. And so we want to know what the patient has. And one of the first decision points, though, is does the patient require hospital admission? So even if the patient's going to be admitted or not, the recommendation is still to collect respiratory specimens and to order the testing for both flu and SARS-CoV-2, at least right now, while all those viruses are circulating. And if that kind of testing is not available, then even just switching over to a standalone COVID test initially is recommended. In the case that the patient is probably not going to require hospital admission, it's still kind of the same recommendations because the signs and symptoms of these predominant viruses, flu A, flu B, RSV, and SARS-CoV-2 are so similar. But here the recommendation for somebody who's not likely to be hospitalized is test them for SARS-CoV-2. And if they're negative, then other testing will depend on the severity of their current situation and what the doctor decides at that time for infection control. But if we look at the bigger picture here, a lot of hospital laboratories and systems have some general respiratory algorithms depending upon if there's an outpatient or inpatient scenario. So that emergency room visit initially could be an outpatient type of scenario, which I have more in detail right here. And many institutions are testing those kinds of patients with high throughput testing as primary testing. They might go to a sample to answer system for overflow or specific patient segments they're interested in. And basically, they usually have a primary system of testing like COVID, flu AB, or COVID, flu AB all together in a miniplex, and then a secondary backup system, right? And they could use that maybe on some other patient populations too of concern, immunocompromised patients and elderly patients, or maybe even just pediatric patients might all be getting syndromic multiplex larger panels. And so the algorithm depends on those patient populations and the testing system that's been implemented in that particular hospital. But switching to inpatients for a moment, there is kind of a different look at that. And that is because those inpatients are more severely ill. They're usually under the care of an infectious disease doctor. Perhaps they're immunocompromised. And so if you're in season there, you might do some primary testing differently before you go to a syndromic panel than you would off season, right? So in season, when there's a lot of respiratory viruses circulating, you might take those more at-risk patients and immediately put them in a full respiratory syndromic panel to make sure that you've identified what's the cause of the symptoms in that patient immediately before you decide to do anything else. But if it's off season, maybe you're going to go to a targeted test. What are the most likely pathogens causing the symptoms in that patient? And of course, there's the in-season and off-season type of a scenario too. That was a thing pre-pandemic. We'll see how things end up as we come out of the pandemic and what hospitals decide to do. But that leads me to be able to talk about the kinds of testing, both miniplex, standalone, and multiplex syndromic panel molecular testing that we have available from DiaSorin Molecular and from Luminex. And so our sample to answer systems for targeted or miniplex testing are shown at the top. The Aries and also the Liaison MDX systems offer COVID standalone, also flu AB, RSV testing, as well as some new combination testing. We have our Simplexa COVID-19 flu AB direct kit under review at FDA right now. And we have our Aries flu AB, RSV, and COVID assay under review at FDA right now as well. So that's targeted or standalone mini panel testing. But if we switch to the syndromic panels, we also have some offerings. We have the Verigene Respiratory Pathogens Flex test available that has about 17 to 18 targets available on it for flexible testing. And we also have the NextTag family of products that can be run on the MagPix. And so that includes the NextTag RPP plus SARS-CoV-2 that has emergency use authorization and includes the SARS-CoV-2 target. And so we have some flexibility that can be offered depending upon the systems and that can meet the needs of the different scenarios of the different hospitals or laboratories, depending upon those inpatient or outpatient types of workflows that I showed in the previous slides. And so with that, I'd like to summarize that the COVID-19 pandemic has definitely impacted the typical respiratory season. RSV and flu have returned, but there sure are shifts in seasonality, and some viral lineages have disappeared, like flu B Yamagata. There's factors like viral interference that might have been a factor in these seasonal shifts, and it could lead, though, that understanding that more could lead to novel antiviral strategies. But vigilance is needed for things like EVD68, vaccine preventable viruses like measles, and even for things like the invasive group A strep. But having the appropriate tests, whether they're targeted or multiplexed, syndromic or standalone, to allow for that flexibility to meet the needs of testing of patients is really a benefit for accurate diagnosis for diagnosing the pathogens causing that respiratory illness. And so with that, I wanted to thank you very much for your attention today, and I welcome any of your questions.
Thank you, Dr. Tab, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. We'll answer as many of your questions as we have time for. Let's get started. Our first question is, non-COVID respiratory illnesses are on the rise, with many causing outbreaks in the US. What are the mitigating strategies the industry is taking to help respond to these surges?
Okay, thank you. That is a really excellent question. So I'll answer from the perspective of Diasormin Molecular and Luminex. So first of all, we don't have a crystal ball, but we've seen these surges. And so we have increased our raw material supplies on hand so that we can respond to these increases. Of course, we are going to continue our surveillance to watch the numbers so that we can increase our production of kits, for example, in step with those increases that we see in terms of surveillance. I would also say that, we should, as I mentioned, keep our eye on the strains and continue to make sure, just in general as an industry, that as these new viruses pop up or different variants of viruses pop up, that our products continue to detect them and that performance is still good.
Okay, thank you. Our second question here. The COVID pandemic has disrupted typical seasonal trends in RSV infection rates. Now that COVID-specific infection prevention measures have largely been retracted, is the expectation that RSV trends will return to normal?
Also a really good question. So I think historically, at least in the Northern Hemisphere, as I mentioned, we always would see RSV come before flu A and flu B. But, and certainly it's back, but it came back a little off-season, a little early, a little bit of a shift. So I think one of my questions is, why is RSV seasonal where it's at to begin with? What are the other things about that virus that we may not understand yet? Like those features like, the droplet theory or viral interference that impact exactly when in the season or seasons of the year it shows up. And so it's definitely back. It's definitely circulating now. But where it ends up, if it'll go back to traditional, space there, right in that late fall or early respiratory season in the Northern Hemisphere, that'd be like the November timeframe. Only time will tell. Once again, wish I had a crystal ball to predict that. But that's just my view on your question.
Fantastic. It looks like we have time for one more question. Is there a concern, given recent measles outbreaks in the US, that other vaccine-preventable viral infections, such as mumps or rubella, are also at risk of sudden outbreaks?
Also an excellent question. I think the answer there is yes. Although measles is the most highly transmissible of those, still the fact that vaccinations have not been up to date, the fact that vaccinations were really impacted, just those usual doctor's visits, those well baby visits, for example, were really impacted by the pandemic. And so I think that there's just great concern in general, and there needs to be better vaccination campaigns within the US, globally, to help protect everyone, because maybe people have forgotten about how bad some of these vaccine preventable illnesses were long ago, because we've all lived in the age here when we have vaccines to prevent these illnesses or these viruses from circulating. And so, I hope people really, get the energy behind, the spirit behind global vaccination campaigns so that we don't have to see a return of some of these vaccine preventable illnesses. So, great question.
Perfect. Thank you, Dr. Tapp. Do you have any final comments for our audience?
Just stay healthy, stay vigilant, and let's continue to try to probably be hygienic too. I'd say wash your hands. Don't touch your eyes, nose, or mouth without washing your hands. Just the typical preventions that we can all have here to keep us from getting respiratory viral infections. Stay healthy.
Thank you again, Dr. Tapp, for your time today and your important research. We would also like to thank LabRoots and our sponsor, DiaSorin Molecular, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.